Welcome back to the latest installment in Shellcode Obfuscation. So, in this installment, we're going to take a look at another encryption routine known as RC4 or ARC4. Now, ARC4 works very similar to the XOR with a multi byte key method that we looked at in the previous example. The way it works is it takes the key, creates a key stream from it, and then XORs your plaintext with the bytes in the key stream. So it's very similar to how we worked before. And let's take a look at just how that is generated. We're going to use a Python script to generate it. So first, we have some code here. You can see that this is based on the Snow Crash RC4 encryption script, who got it from this HSaurus 5 gist. So we're going to open up an input file. We're going to generate a random key, and then we're going to encrypt our data. And there's a few different things that are happening here. We have to create what's known as a key schedule. We have to take and generate a stream from a list, and we need to encrypt our data. So I'm not going to go over in detail how this code works, but if you want, you can read the example on our GitHub. I'm just going to show you that it does print out data. So here now we've generated a random key and we have our encrypted data. So let's go ahead and take a look at our Windows VM. And I want to show a few things. First, a lot of this code is based on Osana Maleth page here. And what's really interesting about this example is this system function 33. That's what's really interesting about the example that we're looking at today. There are two undocumented system calls called system function 32 and system function 33. And the way these work is they essentially implement RC4 encryption and decryption. However, uh, RC4 is essentially like the XOR, in which that if we encrypt something with a key, we can then encrypt it again with the same key to recover the plain text. So you can use system function 32 or system function 33. I'm going to use system function 33 here. So this code, we need to define a new type that returns an NT status. And you can see it's got two structs. It's pointing to a memory region and a key pointer. And then we have our call that we're declaring it. We're saying we want to use this call here. We have our key. We have our encrypted bytes. And this works a little bit differently than what we did before. We actually need to allocate a buffer to store this memory in, or store this shellcode in. And then we're going to copy in our shellcode into that buffer. And then we're going to create a new struct from our key. So we'll create a new struct from our key, and we'll create a new struct from that buffer that we allocated here. And then we're going to call system function 33. And this will decrypt the memory in the buffer for us. And then we're going to iterate through that buffer and print out the output. So if we were to do that, we can see it prints out FC 48, 83, so on and so forth, ending in FFD5. So it's working exactly like we would expect it to. And if we test it with Defender, let's see if that has a detection. And it doesn't. So we're going to upload this to VirusTotal and see just how it works. Well, we got to confirm that we're not a robot, so apparently we're going to have to do this again. So right out of the gate, we see that CrowdStrike detects it definitely. Well, CrowdStrike and Elastic, and there's a few others that are going to detect this. So it's not terrible. It's not great, but it is not the worst example that we will see here. So 7 out of 72, about 10% of the engines detected this. What's really nice about this, however, is that we can use this undocumented system function call to do the encryption and decryption for us. So that's something that could be handy for us. It's a neat trick. So there you go. That is RC4 or ARC4 encryption that we can use in our program to obfuscate and hide our shellcode.